Hello students, in today's video we shall see something on inorganic chemistry, that is unit 6, general principles and process of isolation of elements. We have seen something on elements. In the last year, that is in the first year chemistry, we have seen a chapter on unit 3 wherein which we have seen something on elements. We already know that there are 118 elements in the periodic table, isn't it? So among these 118 elements in the periodic table, around 90 to 92 elements are purely metals. As you can remember, the elements which come under S block, the elements which come under D, F and few elements which come under P are metals. Now in this chapter, we are going to isolate some of the most important elements or metals which we use in our day-to-day life. Now, why is it necessary to isolate these metals? Think of that. See, we use many materials whichever are very common to us in our day-to-day life. We can see buildings made up of iron. We use lot of utensils in our kitchen. The wires which are used for transmission of power, the car we drive, the material made up of that car, or the gold or any ornaments what we wear, all are usually made up of metals, and hence it is very important to isolate those metals. We will not get metals directly, isn't it? So we have to search for those metals in the form of ores or minerals. So this chapter is mainly dealt with those things wherein which we isolate or separate the most important metals what we need for our day-to-day life. In order to introduce the chapter, we just want to know few concepts whatever are given over here. In that concepts, I have 4 important terms. So first term whichever is used here is minerals. Okay, I hope you might have heard about these minerals in your previous classes. So second one is ores, the next one gangue, this is also called as matrix, and the last one metallurgy. Now we shall see what exactly are these. Starting with the minerals. See, minerals, they are those chemical substances which are obtained in the earth crust by mining. Naturally occurring substances, chemical substances which are obtained by mining. They are collectively called as minerals. Okay, I hope you are clear with the concept of minerals. The next category of ores. See, ores are those minerals, they are the minerals only. But using this ores, we can isolate or separate the metal whatever we want. So they are the minerals from which metals can be extracted or isolated. But students, remember 2 important things are here. So one, we should extract the metal. The procedure employed should be economic to us, that is economically and conveniently. See, we have a method and that should be of a low cost to us. If we want to extract and which costs us too much, we don't go for that ore. And even at whatever the method we apply here, it should be convenient to us. Convenient in the sense it should be easy to use. If the method is so difficult, and who is going to adopt that, isn't it? So ores, they are those minerals, so from which the metals can be extracted, or in simple way isolated or separated. That method should be economic to us, economically as well as conveniently. Okay. Then the next one is gangue, or it is called as matrix. See, now I have identified the ore. Directly will we get the metal? No. It contains certain impurities or unwanted materials. So all those unwanted materials present in this ore is called as gangue. Now what may be the unwanted impurities? You might have thought all those things, isn't it? Unwanted impurities, these impurities may be sand, mud, clay, stone, etc. So whatever those unwanted impurities, where should be there? They should be present in the ore. So all those unwanted impurities or the materials whichever are present in the ore are collectively called as the gangue or matrix. And the last concept of metallurgy. Now what exactly is metallurgy? See, a main scenario is to get the element or metal of our use. So from where do we get? We have to get it from the ores. But directly from ores do we get? No. We have to apply certain procedure. So all those scientific, the entire scientific and technology, we should make use of technology also, right? Technological steps or process or methods employed or used in the isolation of the metal. So all those steps whatever we use in order to isolate the metal from its ore, and that all steps come under the common heading of metallurgy. So students, these are the 4 important terminologies what we use in the beginning, and you should be very particular regarding these. You should know. So we have minerals, they are naturally occurring substances which can be obtained from mining, and we have ores, they are those minerals from which the metals can be extracted economically and conveniently. Gangue are all those unwanted impurities whichever are present in the ore. And finally metallurgy, it is that scientific as well as technological steps or procedure which is employed in the isolation of the metal from its ore. Now using these points we shall get into the syllabus. Now in these things there are 3 major steps employed to get the pure metal. Now all those things have been detailedly explained in this chapter. If we are thorough with all those things, then we are at the end of this chapter. Okay. So what are those steps? So now I'll just tell you in brief, but I'll explain the things later on. Okay. The steps whichever are employed in the process of isolation of elements or in the process of metallurgy is, there are majorly 3 steps. So the first one is concentration of the ore. We have to concentrate the ore, which is called as concentration of the ore. And the second one is conversion of this whatever the concentrated ore we get into crude metal or impure metal. And lastly, what impure metal we get? We have to refine that, purification of the metal. Okay. So the entire chapter deals with all these 3 steps. Once if you are thorough with these 3 steps, we are done with this chapter. What is that? We concentrate the ore, and we convert that concentrated ore into its crude metal, and finally we purify that impure metal to get pure metal. I hope you are clear with these 3 steps. So we will get into this. So prior to that, we have certain things. What is the abundance, or where do we get these metals as such? So we will see something in the occurrence of metals. So we know there are many metals, as I have already said, around 90 to 92 elements are metals are present. So in that, how are they obtained? So the next concept is on occurrence of metals, and I have said minerals and ores. Now you may ask, madam said minerals and ores, but she didn't give us any example, isn't it? Because examples might make you more clear. So in that case, we'll just see something on occurrence of metals. Now occurrence in the sense how they are obtained in the earth crust, or in what percentage are they present in the earth crust. Okay. In that case, so the first most abundant element is aluminium. Suppose if you take a metal and if you rank, give them the rank, in that case aluminium will come first. Okay. It is a most abundant metal. So if you just see on all elements, if you compare metals, non-metals, noble gas, everything, if you consider in that case, aluminium will rank 3. So rank for aluminium will be 3, but in metals, okay, if you speak on metals, aluminium will rank first. It is usually seen, you might be knowing, it is usually seen in the form of bauxite. Then next, who comes next to aluminium now in the case of metals? So next to aluminium we have iron, Fe. So this will rank 2. So I will be very specific. So here it is in the case of rank 1 in the case of metal, and it ranks 3 in the case of all elements, don't get confused. Okay. So aluminium will rank 3 in compared with elements, and it ranks first in the case of metal, and second rank goes to iron. So you might be knowing more ores of iron, that is hematite, magnetite, etc. I will write it shortly. Then next, after this iron, we have copper, Cu, and next zinc, Zn, and so on. Now in this chapter, we usually deal with these elements, that is the extraction of Al, iron, copper, and zinc. Now a table has been given in your text, so I am not going to draw table as it is. So we will just list some of the minerals for this aluminium, iron, copper, and zinc along with their composition, as these compositions may also be asked, so you might have to remember these compositions. Okay. So in that case, first one we will write for aluminium. As I have already said, aluminium is usually seen in the form of bauxite. So we will just list out the ores of different elements, list of ores. Okay, sorry, we will write it as minerals and then we will identify the ores. So list of minerals for various elements. Suppose if I take aluminium, symbolic representation of aluminium is Al. So for aluminium we have 2 minerals. So in that first one is bauxite. I hope you might have heard the name of this bauxite. So with the composition AlOX OH 3 minus 2X, where X can range from 0, less than X, less than 1. Students, generally we don't write this formula whenever we say something on bauxite. We simplify it taking Al2O3 dot 2H2O. It is a hydrated molecule of alumina. This is alumina or aluminium oxide. If you can remember this, you just remember this, or else it is okay if you write Al2O3.2H2O. In some cases we even don't write that water also, we just write it as Al2O3. Okay. So one is bauxite and next one is kaolinite. So kaolinite is usually seen in clay. You might be doing some clay models and all, isn't it? So in that we usually see this kaolinite, and this has the composition of Al2OH 4 times Si2O5. For aluminium we have only two major minerals, one bauxite and the other kaolinite with these compositions. Okay. Now this has been over. Next, if I go to the next important metal, which is nothing but iron. Now let us list out the minerals for iron. So you might have heard about the name of hematite, isn't it? So for iron there are lot many minerals are possible. So let us list one by one. So in that case, so first comes hematite. So hematite with the formula Fe2O3. Next, after hematite we have magnetite. Magnetite with the formula Fe3O4. Next, siderite. Siderite is the one that is carbonate ore of iron with the formula FeCO3. And lastly, iron pyrites. Iron pyrites with the formula FeS2. So iron containing sulfur, or it is a sulfide ore of iron. So the first two, that is hematite and magnetite, are the ores or minerals of iron containing oxygen. We say it as oxides of iron. On the other hand, siderite is a carbonate mineral, and iron pyrites the one which contain sulfur. Okay, these are the minerals for iron. Then next one, if I move on to copper. So for copper, still there are more minerals for copper, which is for at a formula Cu. For copper we have copper pyrites. So similar to that of iron pyrites, so here it is CuFeS2, copper pyrites. Also we have cuprite. Cuprite is an oxide ore of copper with the formula Cu2O. Copper glans. So this copper glans is again a sulfide ore of copper containing Cu2S. Malachite, you might have heard about this. It is green in color. We usually say malachite green. So malachite is the composition of copper carbonate CuCO3 along with copper hydroxide CuOH twice. Okay, these are the four minerals for copper. Copper pyrites CuFeS2, cuprite Cu2O, copper glans Cu2S, malachite CuCO3.CuOH twice. Okay. Then the last one what we noted earlier was for zinc. So let us list out the minerals for zinc. So for zinc with the symbol Zn, still we have three different minerals for zinc. So one is zinc blende. Some call it as blende, whichever is convenient for you, you can call it as such. So I usually pronounce it as zinc blende. This is a sulfide ore of zinc with the formula Zns. Next I have calamine. You might have heard something about calamine lotion, isn't it? So in the same way it is calamine with the formula ZnCO3. It is a carbonate ore of zinc. And last one is zincite. It is an oxide ore of zinc which is ZnO. So now zinc blende, Zns, calamine, ZnCO3 and zincite ZnO. Now students, we have listed all the minerals for these 4 different elements, isn't it? We have listed for aluminium, Al, we have listed for iron, Fe, we have done it for copper, and lastly we have done it for zinc. Now in order to isolate or extract these metals from these minerals, we have to select one particular ore. We know that ores, they are those minerals, so from which we have to extract the metals economically and conveniently. Now we have made a list whom to select. So that question is there. Now in this case, for aluminium, so the better ore used here is bauxite. You may be asked a question, name a chief ore of aluminium. In that case, you will write it as bauxite. For iron, we have listed, if you remember, I have listed it as oxides of iron, which are hematite and magnetite, or we can write carbonate, that is siderite, iron pyrite. So for iron, it is usually we write oxides of iron. Usually we consider hematite. Okay. We consider hematite as a chief ore for iron. So why we don't consider sulfide? Because it contains impurities like sulfur dioxide gas, and hence that is not considered. Now for copper and zinc, so there is no particular ore as such. So whichever is present in large quantity, that is taken. Suppose if you take, if I have more of copper pyrites, take that copper pyrites and isolate copper. Or if you have more of copper cuprite or something as such, okay, you take that and isolate. So even for zinc also, usually it is extracted from zinc blend, but if you find more of zinc carbonate or zinc oxide, you can take any. So there is no particular ore for these two. Okay, you can take for copper in general, you can take copper pyrites, and for zinc in general, you can take zinc blend. So this is regarding all those minerals and the chief ores, so from which we can isolate or extract that particular element required for us. Okay, so next we'll proceed. We have come to know something on minerals, ores, gangue, metallurgy. We have listed all those minerals and we have listed the ores. Now we'll get directly into the procedure. So our main task is what? We have to isolate the metal. So in that case, I have already mentioned 3 steps, isn't it? Which are they? Conversion of the ore, that is concentration of the ore, conversion of the concentrated ore into crude metal, and in the lastly we'll purify those metals. So we'll stick on to the first one, that is concentration of ores. The first method applicable in metallurgy, so I'll write it in Roman number 1 for my clearance. So concentration of the ores. Now what do you mean by the word concentration? Is it the one which we use in English? We'll ask, hey, concentrate in the class. Is that of that type? No. And you have already studied the term concentration in the first year chemistry classes. Concentration expressed in terms of molarity, molality. Is that? No. So this is another one. It is not the one which is applicable to English word meaning. In order to US you have to focus. No, it is not that concentration, or it is not the one to express our concentration of the solution. No. So this is something new. I have already said one term in the beginning, which is nothing but gangue. I don't want that gangue in my metal. So the procedure, whatever is employed in the removal of that gangue, is called as concentration. Okay. So concentration, it is the process of removal of unwanted impurities. I can say it as impurities or materials, you can write, present in the ore. So those impurities I have already said, those may be sand, mud, clay, stone, etc. So we have to remove all those impurities, whatever we don't want in that particular ore, and that process is called as concentration. So this concentration of ores can also be called as benefaction. You may be asked, what is benefaction? Benefaction is nothing but concentration of the ore only, or it is also called as ore dressing. We get ready for colleges or schools, isn't it? You get up, you have your bath and thing, and you just get ready. In the same way, the ore will be dressed up. Dressed up in the sense, it will be removed with all the unwanted materials present in it. See, before going to concentration, see what we have, that ore. So that should be powdered first. That is the very first step. So we select a particular ore and it is powdered and kept by using a crusher or something as such. That powdered ore is taken and then it is subjected to concentration. Now this concentration of ore can be done in 4 different methods. There are 4 methods, and all these methods depend on certain differences in the physical property of the ore and the impurity. Okay, that differences will be made note of, and using that differences we can employ different methods to separate all those unwanted materials present in that particular ore. So let us list out the steps now. There are 4 methods. So in the first method, it is hydraulic washing. First method, hydraulic washing. Second one, magnetic separation. Next, froth floatation, and last one, leaching. Okay, hydraulic washing, magnetic separation, froth flotation, and leaching. So we shall discuss about these 4 methods in detail now. Now first I will take up hydraulic washing. So we are in concentration of ores, remember, that the first one. So what happens in this hydraulic washing? See, for this let me give you an example. At your homes, your mother might be preparing rice, isn't it? She will prepare rice. What will she do? If you think she is doing it in a cooker, it will be easy for us. What will do? She take a cooker. Then count the number of members in the family. If there are 4, she may take 2 glasses of rice. You imagine 2 glasses. What will she do? Directly she will put water and then she will keep it to cook? No. What will she do? She will put some water onto that rice and she will just rub all those rice particles and she will thrive that water. If you observe that water, if you use white rice, you can see that in the initial stages of washing, so all those dust particles whichever are present in that particular rice are washed away with water. Will she do it only once? No. She will do it either 2 or 3 times until water what we take will be very clear. So in the same technique is applied here for hydraulic washing also. So there your mother will rub it with the help of your hands. But here we don't do that, we have a separate arrangement for that. Okay. So the first one, hydraulic washing. Now what is the principle lying behind this? I hope you are clear with what the example I gave there, right? So there what happens? The particles or dust particles which were present in rice were of light weight. What happened when water was added to that, all those dust particles were washed away with water. Rice will go out? No. Rice will stay in the cooker itself because it is heavy. So this is a principle. So here also we use the same principle, that is the differences in the gravities of the ore and impurity. Usually impurities will be lighter, so when washed with the current of water or with a stream of water, what happens? All those impurities are washed away with water and leaving behind the ore as it is. So since the ore particles are heavier, they settle at the bottom and ore, whatever all those impurities are washed away. Okay, so the principle used here is differences in gravities of ore and impurity. So usually impurity will be of lightweight, impurity will be light in weight, lightweight, and your ore particles are will the heavier. So whenever all this ore, so it is washed with water. So what happens on washing with water? Impurities are washed away with water. So they are washed away. So we are leaving with pure ore, or all those unwanted materials or impurities are removed. So this is something regarding hydraulic washing. So this, since it depends on gravities of differences in gravities, this method is also called as gravity separation method. You may be asked, what is gravity separation method, or what is the principle lying behind this technique? Gravity separation is nothing but hydraulic washing. Hydra means water. So in that case, the ore is washed with water, impurities being light are washed away, or being heavier settles at the bottom. Okay, so if you can remember the example of washing the rice, what I have said you. Okay, the next one, magnetic separation. Now as the name itself says, magnetic separation. So here we make use of a magnet. So this technique usually depends on the principles of in the differences of magnetic property. The principle lying here is the difference in magnetic property. So either the ore should be magnetic or your impurity should be magnetic. So there should be differences in the magnetic properties of ore and impurity. So that is very clear, I hope. One should be attracted towards magnet. So for this we have a small diagram over here. So what we take is, we take two magnetic rollers, we take two rollers. Okay, so in that two rollers, what I do is, one will be magnetic in nature. So for my convenience, I will take this as a magnetic roller. I will name it as magnetic roller. So this is magnetic and this is non-magnetic. So the two rollers run by means of a belt. So that is a conveyor belt. We want the wheels to move, isn't it? So they are used with the conveyor belt. Now what I do is, I take the powdered ore. So I will take this powdered ore in a cone, something like this here. So and I make that powdered ore to run on this belt. Okay, so here I go. Now what happens? Now you imagine ore gets attracted to magnet. So I will mention it as ore being magnetic, and the impurity whatever present, it does not get attracted to magnet, and I will take it as non-magnetic. Okay, so ore is magnetic, that is, that gets attracted towards the magnet, while impurity, it is non-magnetic, that is, it does not get attracted to the magnet. Now I have in this powdered ore, I have everything. So this is my powdered ore. Now once this is fed on to the conveyor belt, what happens? Now if you just observe carefully, so all those impurities, they are not attracted by the magnet. So once they come along with the belt, and they just, what happens, they fall down like this. So I have a container here to collect all those things. Suppose if you imagine the ore particles, they are magnetic or they get attracted towards the magnet, what happens? So they come along with the roller like this, they come along with the roller, they will come. Now here it gets ended, the magnetic property will get end, what happens? And they will be moving on the belt, isn't it? So once they cut short of the magnetic roller, they directly fall below. So they will fall here. So I have a container here and I will collect all those particles here. Okay. So this will be for, now if you just write this, whatever I collect, which will fall far away from this magnetic roller, they are all impurity, and the one we collect nearer to this magnetic roller, it is our ore. So I have taken ore magnetic and impurity non-magnetic. Remember, if you vice versa, like you just take impurity being attracted towards magnet and ore being attracted, it is not being attracted towards magnet, in that case here comes the ore and here will be your impurity. I hope you are clear. So we take two rollers, of which one will be the magnetic roller. The two rollers are connected by means of a conveyor belt, and in that case I will take a powdered ore in this cone arrangement, and powdered ore is made to fall on the conveyor belt. So impurities, when they are not attracted towards magnet, they are collected far away from the magnet. On the other hand, ore particles which are being attracted towards magnet, they stick on to this magnetic roller, and finally once that roller ends and the belt moves on, they fall down and they are collected nearer to the magnetic roller. Okay, we have seen magnetic separation, hydraulic washing. Next, the third one. So I have already drawn a diagram for you, the schematic diagram here. So what was the third one? So the third one was froth, floatation method. So the name itself says froth. So what does that word mean? So froth is nothing but, so to simplify the concept, now if you want to wash your clothes, what we generally do, we take some detergent powder, we put in a bucket and we add water, isn't it? Now you want to get froth, what we do? We put our hands and we'll just shake it. So enormous froth will come onto the top. So that itself is froth. So the same concept is applied over here. So in this froth flotation method. So students, this froth flotation method is applicable only for sulfide ores. So do remember, the ores which contain sulfur can be concentrated by this method. We can't take any other ores. Okay. Now what exactly is done in this method is, see, they generally take a tank which is something like this. Okay. The powdered ore is taken in the tank and it is filled with water. That is, a suspension of the powdered ore in water is taken. Collectors are added. Now what are collectors? See, collectors, they enhance the non-wettability of the ore. So usually the collectors what we add here is, they may be pine oil, oil in general, fatty acids, etc. Okay, so the thing added over his collectors, they enhance the non-wettability of the ore. So we add that. I have written as oil there, we can see. Then stabilizers are added, that is froth stabilizer. Now what is the lifetime of a froth? Will it stay for a longer time? No, isn't it? Hardly a minute, hardly a minute. Now whatever that froth arises on the top, that should stay for some time. So in that case, we add some froth stabilizers, that is they stabilize the froth. Whatever the froth which comes on the top, it is stabilized by adding froth stabilizers like cresols, aniline, etc. Okay, so I have taken the suspension of the ore in water. To that I have added collectors like phenol or fatty acid, anyone you can add. Then to stabilize the froth, I have added froth stabilizers, small amounts of cresol or aniline. Then you can see here I have a rotating paddle, because I have already told whenever you add detergent, we have to, in order to get more of froth, what we do? We put our hands and we just shake it. We get, meanwhile that powder, whatever we add, detergent or something as that also gets dissolved and we get enormous amount of froth. In the same way, a rotating paddle is inserted into this tank. That rotates, to fro motion will be there. What happens? During that rotation, it will pump in some air into that tank. Due to that, more froth comes to the top. Okay. So here I have that rotating paddle. What they do, that will draw air and it will stir the pulp. So pulp is nothing but you have all those ore with collectors and all those things. Now once the froth comes, now what is the speciality in this? So once the froth comes, it will come along with your ore, which is nothing but the sulfide ore. Okay. So froth, what does it contain? This contains the ore. Impurities all settle at the bottom. They don't come along with the froth. They will stay somewhere here. All those impurities settle at the bottom. On the other hand, froth while coming up, it will ask that, hey, ore, come along with me, let's go. So what happens? That will come. I have written here in a different color. You can notice that. That is the mineral froth. Okay. So the same thing, what we can see over here also. In this froth flotation method, it is applicable for sulfide ores. We add collectors which enhance the non-wettability of the ore, and we add froth stabilizers which stabilize the froth. There is a rotating paddle which rotates and draws some air into it, creating more of froth. So froth while coming up will come along with the ore, and thus we have separated the ore from the impurity. Finally, once this is reached, we can easily skim it off. It is similar to your mother's doing some buttermilk and getting butter, isn't it? So once they churn that buttermilk, what happens? Or that butter will come on top, and finally we can remove that butter and we are left out with buttermilk as such. Okay. So this is how we remove sulfide ores from its impurities. Now if you just think, I have two different sulfide ores. Can I separate by this method? I have already written one example of sulfide ore, which was ZnS, and I will take one more, which is lead sulfide, or it is also called as galena. Now, is it possible to separate these two? How do I separate the two now? Can I separate by froth flotation? Yes. We can separate two different sulfide ores by froth flotation method. So we can do it by two methods, either by adjusting the water to oil ratio. If you just adjust water to oil ratio, we can separate the two, or by adding a depressant. This can be asked, name the depressant used, something as such. So the depressant can be added. Now in order to separate these two, that is zinc sulfide and lead sulfide, the depressant added is sodium cyanide. So with the formula NaCN. Now what will this sodium cyanide do, or how will it separate the two? Now what this sodium cyanide does is, now froth will come, the technique is all same. So we'll add small amounts of sodium cyanide, that's it. We have all this will go into the tank along with few amounts of sodium cyanide. Now this sodium cyanide, what it does is, it will pull the leg of zinc blend. It will say, hey zinc, you don't go, you sit with me, you sit with me, you sit with me. What does it do? So it will prevent the zinc blend to come along with the froth. The zinc will say, PBS, this being sulfide ore, this will go along with froth. It will tell, froth, I'll come. It will go. But this zinc blend also wants to go actually. But what happens? What this sodium cyanide? It will not allow the zinc blend to come along with the froth. It will prevent, hey, you don't go. It will make a check. Your zinc blend, no, you sit here. Your PBS, you go. So what does it do? So it will separate the two. This sodium cyanide, this will allow PBS to come with froth. It will allow, yes, go. But it will not allow or prevents ZNS to come with froth. Students, you may be asked a question, what is the role of sodium cyanide in the separation of, what is the role of sodium cyanide in froth flotation? What does it do? So it helps in the separation of two different sulfide ores, or it allows PBS to come along with the froth, thereby preventing ZNS not to come along with the froth. So you can be asked, or you may be asked to name the depressant, which is nothing but sodium cyanide, or you can write the formula NaCN, something as such. This is how we can separate the two different sulfide ores. Okay, so this is regarding froth flotation method. That is the third one. Next, we will move on to the last method of concentrating the ore, which is nothing but leaching. So leaching is applicable for all those ores which are soluble in a particular solvent. So if you take a particular solvent in which those things are soluble, we make use of the procedure which is nothing but leaching. So the principle is ore soluble in a particular solvent. We have to select one particular solvent, in that the ore should be soluble. Now here one good example given to you is leaching of bauxite. Very important concept, as I have already said, we will be dealing with aluminium, iron, copper and zinc. So here comes our aluminium now. Leaching of bauxite. We will remove all the impurities present in bauxite by leaching. Our concentration of bauxite is done by leaching. Now what exactly the procedure is? The procedure involves 3 steps. Once again, there are 3 different steps over here. Now prior to that, we want to know what are the impurities present in this bauxite. The impurities present are silica, which is nothing but sand or SiO2, oxides of iron, it can be anything, oxides of iron, maybe Fe2O3, FeO, Fe3O4, anything, and TiO2, titanium oxide. These are the major impurities whichever are present in bauxite. Okay, now what we do? We will take one by one. First step, what is done is we will take this bauxite. Okay, the bauxite is concentrated by treating this bauxite with sodium hydroxide solution. Okay, I will just in brief, bauxite This is taken and this is usually digested or concentrated by using sodium hydroxide solution. You can take concentrated sodium hydroxide solution and it is leached to sodium aluminate. Okay, bauxite is converted into sodium aluminate by treating with a concentrated solution of sodium hydroxide. Just the reaction is not that simple, students. This requires certain conditions of temperature and pressure, which is very important. You have to mention those. The temperature what we mention here is around 473 Kelvin to 523 Kelvin. 473 to 523 Kelvin temperature and a pressure of 35 to 36 bar. If you subject to these conditions of temperature and pressure, the bauxite ore gets converted into sodium aluminate. Now we will write the equations. So we will take bauxite. As I have already said, for the sake of simplicity, we write bauxite as Al2O3. Okay. This bauxite is treated with sodium hydroxide. What is the formula? Sodium hydroxide is NaOH. Sodium hydroxide, I said it as solution. Solution in the sense with water, H2O. What am I going to get? I am ending with sodium aluminate, sodium NaAlOH 4 times. Now, if you balance this, see, remember students, in inorganic chemistry, the equations whatever you write should be compulsorily balanced. Unbalanced equations do not carry marks. So remember, practice it and then write. Okay. So if you just look into the equation, I have 2 aluminum atoms here and I have only 1 over here. So what should I do? I have to multiply this by 2. Once this becomes 2Na, I have to make it as 2Na. Now you balance the last thing either on hydrogen or oxygen. Finally, we'll end up with 3H2O. You can just cross check, the equation will be balanced as such. So bauxite treated with sodium hydroxide solution. Solution is nothing but water. We end up with sodium aluminate. So I have written on the top, so I am not going to write it again. This is sodium aluminate. So this first step is over. I have to take a temperature of this one, 473 to 523 Kelvin temperature, and a pressure of 35 to 36 bar. Okay. So I have converted bauxite to sodium aluminate. Now in this case what happens is, what happens to these impurities now? We want that also, right? Now in this case SiO2, whatever that silica is there, right? So that gets converted to sodium silicate. While rest, they do not react with sodium hydroxide and they are removed. Rest impurities, they are removed. Only I am left out with the silica, which is present as sodium silicate. Now along with sodium aluminate, I also have few amounts of sodium silicate. So I have to remove this now. Okay. So I have ended with the first step. In the second step, what we do is, we take this now. I have ended with sodium aluminate, isn't it? So I will take that sodium aluminate. That sodium aluminate is neutralized with by passing carbon dioxide gas. We will neutralize this sodium aluminate. So this is neutralized by passing CO2, carbon dioxide gas. We will write that equation also. We have this sodium aluminate, take it as it is, NaAlOH 4 times square bracket close, we pass CO2, carbon dioxide gas. What we end in this case is, we end with Al2O3 dot X molecules of water. So we end up with hydrated alumina. The value of X varies, maybe 1, 2, 3, something as such. So we will take it as X only, hydrated alumina. So along with this, now sodium has to come out, right? And we have to make use of this carbon dioxide also. So that will come out as NaHCO3. Okay. Now we have to balance this again. It is not balanced. I have Al2. I have 2 aluminium atoms, and here I have only 1. So we make it as 2. And I have 2 Na. We'll make this as 2. So that gets balanced. So don't worry, since there is X H2O, so it is not a problem. In the second step, whatever the sodium aluminate we have obtained in the very first step, it is treated or it is neutralized by passing carbon dioxide gas, and we end up with hydrated alumina, and it is separated along with sodium bicarbonate. Last year we have studied that preparation and properties, etc. So we might be knowing NaHCO3, which is removed. See, once we want to get this hydrated alumina, what we do is we add a few freshly prepared alumina that is also added just to enhance the reaction. Okay, small amounts, not too much. So in order to favor precipitation of this alumina, small amounts of freshly prepared alumina is also added. Now in this case what happens, the sodium silicate will remain as it is, that is usually purified or removed in the next step, or we will move on to the last step over here, that is the third step, wherein which whatever the alumina we have obtained, I want this only, isn't it students? I want only Al2O3. Now my main intention is to remove this H2O. What should I do? How will I remove the traces of water? Just heat. So it is separated by filtration and then it is dry. So hydrated alumina so this is separated and dried. So it is dried at some high temperature to get pure alumina. So we will end up with pure alumina just by drying this hydrated alumina. So you take that again, the same thing, Al2O3 dot hex H2O. We are not treating anything here, no reagent comes into picture, we are just heating, symbol of heat is delta. Heated with certain higher temperature of 1470 Kelvin, 1470. What happens? You have to replace this dot by a plus sign. I will end up with Al2O3 plus H2O. How many molecules? X molecules of H2O. So this is how we separate all those impurities present in the bauxite ore. So here sodium silicate that will remain in the solution itself, it will not be dried, and hence that can be easily removed. So this is how we concentrate bauxite ore, that is leaching of bauxite. So I will just repeat. So bauxite, it is digested in a concentrated solution of sodium hydroxide at a temperature of 473 to 523 Kelvin under a pressure of 35-36 bar pressure, and has been converted to sodium aluminate. If I have silica, it is converted into sodium silicate, while rest impurities, they do not react and they are removed. So here comes the balanced equation. And in the second step, whatever the sodium aluminate is formed, it is neutralized by passing carbon dioxide gas, and we end up with hydrated alumina. In order to enhance the precipitation, a few freshly prepared alumina is added as a seeding agent, and we end with hydrated alumina. And in the last step, that hydrated alumina, it is separated and it is dried to end up with pure alumina, which requires a slight higher temperature of 1470 Kelvin, and we end up with pure alumina. So bauxite has been converted into pure alumina. You may be asked questions like this: explain leaching of bauxite. You can easily write 3 different steps, or in which they can also ask how do you get pure alumina from bauxite. They are not mentioning the procedure here. They will just ask how will you get this pure alumina from bauxite. In that case also you can mention the same 3 steps. Okay. So this is one example given in the case of leaching. One more example is given to you students for leaching. In that case is extraction of gold and silver. No much details have been given to you here. A small bit is told. In the extraction of second example is extraction of gold or silver. So we know gold and silver, the noble metals, so they do not react with any other things what we wear and all, right? We don't have any reaction. They are noble in nature, unreactive. Now how to separate this gold? So what generally we do is, here whatever the solvent we use here is either sodium cyanide, I have already mentioned, NaCN, or potassium cyanide, KCN. Any one you can take. If you are interested in NaCN, you take that, or potassium cyanide, you can take this. So we dissolve the gold in this one, but solutions of these two in the presence of air. It is very important, in the presence of air. Now if you write the equations, I have gold, or in simple I will take it as M, where this M can be gold or silver. So you will dissolve this in cyanide. So for the sake of simplicity, I will write it as cyanide ions. Either you can take NaCN or KCN, you remove this minus sign and write that Na or K. So cyanide solution, I said, solution in the sense we make use of water, and in the presence of air, air is nothing but oxygen. What happens in this case? See, in this case, this metal where this M, I will be specific here, where this M can be gold, so gold symbol is Au, or it can be silver, which is nothing but Ag. Now in this step, when treated with cyanide, they end up with a complex of gold with cyanide. So I have metal Cn twice minus plus I have water and others, so I will be ending with hydroxide ions, OH minus. So we need to balance this. So we usually balance it by writing a simple way. What I remember is, you just remember 4, double it, will end up with 4 plus 4, 8. Take this 4, divide it by 2, we end up with 2. So this is the way I remember. Okay, you can balance it by using oxidation number method. You can have a try in that method also. Okay, so first I will write it as 4, divide that 4 by 2, we end with 8. Say consider the same 4 and multiply it by 2, and for H2O you divide that by 2. Now what, for oxygen, no, oxygen is only 1. Now next it is simple, you can just see how many M is here, there are 4. So I have only 1, so I have to write here also it is 4, and even OH is also 4. This is the first step, wherein which gold is converted, gold or silver is converted into its complex. Then we will take the same one here. I want the metal, isn't it? I don't want that complex and all. So my main intention is to get the metal only. I don't want anything else. So I will take this and I treat it with the metal, just simple displacement reaction. So I will take it with zinc. So now zinc will displace this metal. So zinc will go and sit in that place. So since zinc is 2 plus, so here I have that Zn bracket open Cn 4 times 2 minus plus, I'll end up with this metal M. Okay, so here we have whatever I've obtained here, we'll take it as 2 and here it is 2M. So here we may not end with pure ones, but majorly we can concentrate, the procedures will be the same and to end up with either gold or silver. So this is the one, much explanation is not given to you, but the thing is they have given you the ionic equations. If you want to make it simpler, you can replace this negative sign by either you can take Na or K. Okay, first one, they are dissolved in the solution of either sodium or potassium cyanides in the presence of air. We end up with the complex, and that complex is treated with zinc, where zinc replaces that particular metal, and we end with pure one. Not pure, then finally it is subjected to purification. Okay, so students, we have done with the 4 different steps of concentration of the ores. Very first step I have selected. There are 4 methods, just recall: hydraulic washing, which makes use of the differences in gravities. Second, magnetic separation, which will make use of the differences in the magnetic properties of the impurity as well as the metal. Froth flotation, an important one, so where in which it is applicable for sulfide ores and it is washed away with the current of water. And last one, leaching, very important for bauxite. It is given 3 different steps: converting into corresponding silicates by treating with sodium hydroxide, then neutralization by passing carbon dioxide gas, and lastly heating of that hydrated alumina to end with purified alumina. So one more example given to you here is over. So we are done with the first part of the metallurgical process, that is nothing but concentration of the ores.